Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like data access optimizations, balance analysis and light speed estimates, storage order. Let's get started. Slide 1. Data access optimization. Efficient data access is one of the most critical factors in high-performance computing, HPC. Even with the fastest processors, a poorly optimized memory access pattern can significantly slow down execution. This is where data access optimization plays a vital role. Key explanation. Data access optimization focuses on improving how data is retrieved, stored, and transferred within memory hierarchy. The goal is to minimize delays, increase cache efficiency, and reduce unnecessary memory accesses. Key points explained. 1. Minimizing cache misses. Caches L1, L2, L3 store frequently accessed data. If data is not found in the cache, the system must access main memory, RAM, which is 100x slower. By organizing data properly and optimizing access patterns, we can ensure maximum cache utilization. 2. Improving memory bandwidth usage. Modern processors have high memory bandwidth, but inefficiencies in data transfer and CPU memory interaction can underutilize bandwidth, leading to wasted cycles. 3. Avoiding unnecessary memory access. Fetching the same data multiple times is inefficient. Instead, store intermediate results in registers or cache. 4. Using prefetching. Prefetching anticipates which data will be needed next and loads it into cache before the processor requests it. 5. Aligning memory access patterns. Choosing between row major versus column major order can have a huge impact on how efficiently the CPU retrieves data. Example. Consider matrix multiplication. If implemented naively, it may cause excessive cache misses, slowing down execution. However, optimizing memory access using row major order can improve performance by up to 10x. Significance. Optimizing data access reduces latency, improves CPU efficiency, and ensures better performance in AI, simulations, and scientific computing. Slide 2. Techniques for data access optimization. Now that we understand the importance of efficient data access, let's explore techniques to achieve optimal memory performance. Key techniques explained. 1. Loop blocking, tiling. Large datasets don't fit entirely in cache. By breaking them into smaller tiles, we can ensure that only small chunks are loaded at a time, maximizing cache reuse. 2. Data alignment. Misaligned memory accesses cause extra processing cycles. Ensuring proper memory alignment improves retrieval speeds. 3. Minimizing strided access. If memory is accessed in large strides, e.g., accessing every 10th element, CPU caching is ineffective. Keeping memory access sequential avoids performance degradation. 4. Software prefetching. Prefetching reduces wait time by fetching data before the processor actually needs it. 5. Efficient data layouts. Optimizing how data is stored in arrays ensures fast memory access and minimal cache misses. Example. If a loop accesses an array column-wise instead of row-wise, performance drops significantly because of inefficient memory access. Significance. By following these techniques, memory-bound computations can be made up to 5-10x faster, greatly improving HPC performance. Slide 3. Balance analysis. Balance analysis helps determine whether a computation is limited by processing power or memory bandwidth. This allows us to identify performance bottlenecks. Key aspects explained. 1. Compute-to-memory ratio. If a processor waits too long for memory access, it is memory-bound. If it fully utilizes available bandwidth, it is compute-bound. 2. Cache utilization. Efficient cache utilization ensures that data is retrieved quickly, avoiding unnecessary RAM accesses. 3. Memory bandwidth utilization. Checking if available memory bandwidth is fully utilized ensures that we are not wasting potential computing power. 4. Instruction execution efficiency. If a CPU spends too many cycles per instruction, optimization is needed. 5. Pipeline stalls. When the processor waits for data instead of executing instructions, pipeline efficiency drops. Example. Modern AI workloads are optimized to be compute-bound, ensuring the CPU, GPU spends most of its time processing data rather than waiting for memory. Significance. Balance analysis helps programmers fine-tune data access patterns and processing loads, leading to better hardware utilization. Slide 4. Light speed estimates in HPC. Light speed estimates refer to the maximum theoretical speed of computations, helping set expectations for performance limits. Key factors explained. 1. Clock speed, GHz, determines how many cycles per second a processor can execute. 2. Memory bandwidth, defines how fast data can move between CPU and memory. 3. Cache performance, lower cache latency results in faster data retrieval. 4. Instructions per cycle, IPC. Modern CPUs execute multiple instructions per cycle, increasing efficiency. 5. Floating point operations per second, FLOPS. FLOPS measures how fast a processor can handle complex mathematical calculations. 6. Latency and throughput. Latency is the delay in response time, while throughput is how much data can be processed per second. Example. If a CPU runs at 3.5 GHz with 4 instructions per cycle, its theoretical peak performance is 14 billion instructions per second. Significance. By understanding these factors, HPC developers can optimize software to achieve near theoretical peak performance. Slide 5. Storage order in high-performance computing. The way data is stored in memory affects access speed, cache efficiency, and overall performance. Key storage orders explained. 1. Row major order, stores rows sequentially before moving to the next row. Best for C, C++, Python, NumPy. 2. Column major order, stores columns sequentially, improving column-wise access. Best for Fortran, MATLAB. 3. Hybrid storage order, a mix of both row and column major for optimization. 4. Array padding, extra space is added to prevent cache conflicts. 5. Structure of arrays, SOA, each attribute is stored separately, improving parallelism. 6. Array of structures, ARs. Data is grouped in structs, making access simpler but slower. Example. Fortran uses column major order, while C, C++ uses row major order. Significance. Choosing the correct storage order reduces cache misses, making matrix computations and AI workloads much faster. Slide 6. Row major versus column major storage comparison. In high-performance computing, the way data is stored in memory has a direct impact on execution speed. The two most commonly used storage formats are row major order and column major order. The choice between them determines how efficiently a program accesses and processes data. Understanding storage order. Row major order. In this format, an entire row of a matrix is stored contiguously in memory before moving to the next row. This is the default storage method in programming languages like C, C++, and Python, NumPy. Best for applications where data is accessed row-wise. Column major order. Here, an entire column is stored before moving to the next column. Used in Fortran and MATLAB, which are popular in scientific computing. Best for applications where data is accessed column-wise. Comparison table explanation. Since modern processors load data in cache-line chunks, accessing memory sequentially is much faster than jumping across memory locations. Choosing the right storage format avoids cache misses, improving performance in matrix-based computations, image processing, and AI. Example. Consider a 1000 times 1000 matrix stored in row major order. Accessing it row-wise is fast because the elements are stored next to each other. However, accessing it column-wise is slow, as it causes frequent cache misses. The opposite applies to column major storage. Significance. Selecting the correct storage order based on workload can significantly improve execution speed in HPC applications. Slide 7. Optimization techniques for storage order. Optimizing storage order ensures efficient memory access and reduces cache misses, which is crucial for high-performance computing. Key optimization techniques explained. 1. Choosing the right format. Use row major order for C, C++, and column major order for Fortran to match the language's default behavior. Avoid unnecessary format conversions, which waste CPU cycles. 2. Loop ordering optimization. Always iterate in the same order as storage. Example, in row major order, access data row by row instead of column by column. 3. Using structure of arrays, SOA, instead of array of structures, ARS. SOA stores each data attribute separately, enabling vectorized processing. Example, AI frameworks use SOA for efficient parallel execution. 4. Padding for alignment. Memory alignment prevents cache conflicts, improving retrieval speed. Adding extra padding bytes between data blocks optimizes access. 5. Avoiding strided access. Strided memory access, skipping elements, leads to poor cache utilization. Ensure continuous access patterns for maximum efficiency. 6. Prefetching data. Modern CPUs predict which data will be accessed next and load it in advance. Manual software prefetching improves cache hit rates. 7. Blocking and partitioning. Divide large matrices into smaller, cache-friendly chunks to avoid cache overflow. Example, changing loop ordering and storage format in matrix multiplication improves performance by 3x in scientific computing applications. Significance. Applying these optimizations ensures minimal memory bottlenecks, faster computation, and better CPU efficiency in HPC applications.